In this video, we'll talk through the notes for section 2.6 on Laplace transforms. Laplace transforms are something that you probably would have encountered in your ordinary differential equations class, so much of this section will be review, but we will apply it to partial differential equations in a way which might be at least new. So we'll start with the definition. Let u be a continuous, or at least a piecewise continuous function on the domain t greater than or equal to 0. When we say piecewise continuous, that actually includes continuous as a subcase because it could just have one piece, but I just wanted to emphasize that it could be continuous or just piecewise continuous. We define the Laplace transform of u using integration. It's an integral operator. The Laplace transform of u is denoted by Lu, or script Lu, and it has an argument usually s, whereas the original function is assumed to have an argument t. We define the Laplace transform of u at s to be equal to the improper integral from 0 to infinity of u at t times e to the minus st dt, provided of course that this improper integral exists. There are certain classes of functions where we know that this improper integral does converge. So we recall that a function u is said to be of exponential order if we can find some constants a greater than 0 and c greater than 0, such that the size of the function at t, or the absolute value of u at t, is less than or equal to c times e to the at for all t eventually. That is, we can find some capital T greater than or equal to 0, such that the absolute value of u at t is less than or equal to c times e to the at for all t greater than or equal to capital T. So eventually, the function u at t is bounded by some exponential function or some constant times an exponential function. We have a theorem that says that if u is of exponential order, then the Laplace transform of u exists. We won't bother proving that in this lecture. Since we usually think of t as representing time, we say that u at t is in the time domain, and the Laplace transform is in the transform domain. The Laplace transform turns derivatives in the time domain into multiplication in the transform domain, and that's what makes it so useful for helping you solve differential equations. So the Laplace transform of the first derivative of u is equal to s times the Laplace transform of u minus u at 0. And the Laplace transform of the second derivative is s squared times the Laplace transform of u minus s times u at 0 minus u prime at 0. So you can see the first derivative is transformed into s times a Laplace transform, with some initial condition. And the second derivative is transformed into multiplication twice, which is why we have the s squared. Now the trade-off is that you end up with these two initial conditions that you need. You can proceed inductively to find formulas like this for any derivative of u. Let's look at an example where we solve an initial value problem. So the initial value problem we're looking at is the second derivative of u plus u is equal to 0. We're going to need these initial conditions because if you look back at the theorem that we just stated, the Laplace transform of u double prime requires u at 0 and u prime of 0. So it requires two initial conditions. Here in this example, we have a u double prime. So when we compute the Laplace transform of that, we'll need u at 0 and u prime of 0. Just for simplicity, we'll let u of 0 be equal to 1 and u prime of 0 equal to 1 as well. So we compute the Laplace transform of both sides. On the left, we have the Laplace transform of u double prime plus u. And on the right, we have the Laplace transform of 0. The Laplace transform of 0 is simply 0. The Laplace transform is linear, so we can rewrite the Laplace transform of u prime prime plus u as the Laplace transform of the second derivative plus the Laplace transform of the original function u. So we use our theorem from above So the Laplace transform of the second derivative is s squared times the Laplace transform of u minus s times u at 0, which is 1, minus u prime of 0, which is also 1. And to this we add the Laplace transform of u. It's customary to assign some other letter to the Laplace transform of u, usually a capital U. We'll be doing that later, but for this problem it's simple enough that we don't do it. So we simplify. We have s squared times the Laplace transform of u minus s minus 1 plus another Laplace transform of u. So if we add those together and we factor out the Laplace transform of u, we're left with s squared plus 1 times the quantity times the Laplace transform of u. Then we put this minus s minus 1 on the other side. So we add s and 1, and so those end up over on the other side. Then we divide by the s squared plus 1 to get this expression. The Laplace transform of u is equal to s plus 1 over s squared plus 1. So we can rewrite this as s over s squared plus 1 over s squared plus 1. These are useful expressions because we know what the inverse Laplace transform is for each of these. So u is the inverse Laplace transform of this quantity. U is the inverse Laplace transform of s plus 1 over s squared plus 1, but we can write that as this sum. So u is equal to the inverse Laplace transform of s over s squared plus 1, which is cosine of t, and we add on the inverse Laplace transform of 1 over s squared plus 1, and that's sine of t. So what that means is that u is equal to cosine of t plus sine of t. One of the nice things about the Laplace transform is how it interacts with convolution. Let's just remind ourselves what convolution actually is. So we start with u and v piecewise continuous functions, or simply continuous functions, on the interval from 0 to infinity. Then the convolution of u and v is the function u star v, defined by u star v at t is equal to this integral. It's the integral from 0 to t of u at t minus s times v at s ds, where t is some number greater than or possibly equal to 0. Of course, if t is equal to 0, then this value is 0. So let's look at an example. So let's let u be equal to t, u at t is equal to t, and v at t is equal to e to the t. So these are simple functions, so to speak. And let's compute the convolution. So u convolved with v, or the convolution of u with v, at t is equal to the integral from 0 to t of u at t minus s times v at s ds. So u at t is equal to t, so that means whatever the input is, the output is the same. So u at t minus s is just simply t minus s. And here we have v at s is going to be e to the s. So this is an integral that will require integration by parts, but it's a very straightforward one. You let u be equal to t minus s and dv e to the s ds. So this is your u, this is your dv, and a little bit of integration by parts will give you that this convolution is e to the t minus 1. So that's an example of convolution. One of the nice properties of convolution is that it's commutative, so u convolved with v is the same as v convolved with u, which is very handy if you happen to forget which order the definition is in. So v convolved with u we can write out and show that it's actually equal to u convolved with v using a substitution. So v convolved with u is equal to the integral from 0 to t of v at t minus s times u at s ds. So what we're going to do is we're going to make a substitution. So we're going to let t minus s be r. So then ds here, this is the opposite of dr. And this us, so that s becomes t minus r. So all of that has been written out here. Of course, we have to change the limits of integration as well. So if s starts at 0, then r is t minus 0 is t, so that's why there's a t there. And then if s is t, then r is t minus t, which is 0, so that's why there's a 0 there. And now we just use this minus sign to swap the order of integration here, and then we'll have the integral from 0 to t of u at t minus r vr dr. and that's just u convolved with v dt. Now notice we have an r here instead of an s, but that's okay. R is what we call a dummy variable. It doesn't signify anything or stand for anything other than the variable of integration. So you could change that to an s and it would be fine. So that tells us that v convolved with u is the same as u convolved with v. And now that brings us to something called the convolution property, which is the main reason that we're interested in convolution right now. So the convolution property says let u and v be continuous or piecewise continuous on the interval from 0 to infinity and of exponential order. That's to ensure that u and v actually have Laplace transforms, or that is to say the Laplace transform of u and the Laplace transform of v do exist. Then the theorem is that the Laplace transform of u convolved with v exists and is equal to the product of the individual Laplace transforms. So in other words, the Laplace transform of u convolved with v is equal to the Laplace transform of u times the Laplace transform of v. So the Laplace transform turns convolution into multiplication, which is a very nice property to have. So we can prove this. Let's do that now. So the proof. So the first thing to do is write out the Laplace transform of u convolved with v, which we've done here. The Laplace transform of u convolved with v is the integral from 0 to infinity of the convolution at t times e to the negative st dt. Now the convolution itself is an integral operator, so this becomes a double integral. On the outside we have the integral with respect to t from 0 to infinity, and on the inside we have an integral with respect to our dummy variable, r, from 0 to t. Here I'm using r as my dummy variable again because I'm already using s for something else. S is the transform domain for the Laplace transform in this case. So the basic idea here is to swap the order of integration, and that's really what this picture is here for, to help us swap that order of integration. So for the first integral, we have the integral with respect to t on the outside. So the idea is that this t is going between 0 and infinity. So we want to pick a t between 0 and infinity. And then we'll choose the r between 0 and t. So r is between 0 and t. This is useful for setting up the picture that you see here. The idea is we pick any t that we want between 0 and infinity. So let's pick it right here. And now r is our vertical axis, and r is going to go between 0 and t. So the smallest r can be a 0, which is on the t-axis. And then it goes up until it hits the line r equals t. That's this line right here. This line is r equals t. So we pick a t between 0 and infinity, so any positive t will do. So here's an example of such a t. So we pick that t, and then we allow our r to vary from 0 up to t, so anywhere on that line. So by picking different t values, so if we pick t here, then r goes up to here, basically what we're doing is we're filling in the bottom triangular region here. Now it's an infinite triangular region, but we're filling all that in. So that's the region over which we're integrating. What we want to do is we want to swap the order. So we want to choose r first. So that means for the second integral, we're going to pick any r that we want. And again, r can be anything between 0 and infinity. So let's pick this r here. Let's pick that r. And now we're going to allow t to vary. Now t can only vary along this horizontal line. The smallest it can be is r. So the smallest t can be is r, and the largest it can be is infinite, like so. So that's what gives us these limits of integration here. So r goes from, let's do it this way, so r goes from 0 to infinity, so that r goes from 0 to infinity, and t goes between r and infinity. So this t goes between r and infinity, like so. So the next step is to make a substitution. So the substitution we want to make is this one right here, x equals t minus r. So if you let x be equal to t minus r, then this thing, t minus r, becomes x. and dx is just dt, so we have that dx is just dt. We also have to change everywhere else that we have our variable of integration. So our variable of integration was t, so all of these t's have to change. So dt becomes dx, t minus r becomes x. There's also a t right there. So t is x plus r. So this one is x plus r, goes right there. And you can see that here. This x plus r is that x plus r. Maybe again, we'll have just a little bit of color coding here. That x plus r is that x plus r. And this dx is that dx. And of course, t minus r is x, is that x right there. Now we also need to change the limits of integration. And for that, we just use our relationship here, this relationship, t equals x minus r. So t starts at r there. So that means x starts at r minus r, which is 0. So that goes to that one right there. And of course, as t goes to infinity, x equals t minus r also goes to infinity. So we still have those infinities right there. So we now changed our limits of integration and our variable of integration into x. Now the reason we're doing that is just so that way we can recognize the Laplace transform on the inside. So what we're going to do is we're going to take this e to the minus s times x plus r, and we write that as e to the minus sx times e to the minus sr, like so. This e to the minus sr doesn't have anything to do with x, so we can actually take this thing and bring it out here. And that's exactly what we did right there, e to the minus sr. So if I wanted to continue color coding, maybe we'll do that one with green, this e to the minus sr is this e to the minus sr. Now everything else is left alone. So in particular, this e to the minus sx, that's that one right there. But notice that on the inside of this integral now, we have exactly the Laplace transform of u. Here we're using x as our dummy variable. This s, remember, that's our transform domain. So this is actually a function of s. So you can actually factor this out now, because this has nothing to do with r. So the only remaining integral is an integral with respect to r. So we factor out that Laplace transform of u, and what are you left with? You're left with the integral from 0 to infinity of v at r e to the minus sr dr. And this is the Laplace transform. Again, that s corresponds to the argument in our transform domain. So we end up with the Laplace transform of u times the Laplace transform of v, which is exactly what we're supposed to get. So it turns out that this convolution property is true, and it's very useful for us when we're solving differential equations. Now, just for the sake of reminding ourselves exactly what some of the Laplace transforms are, I've included this table. This is from our book, from Logan, and basically I've just taken a screenshot and put it here. But this is from the book. So this compiles some nice Laplace transforms that we'll need. One thing that I want to remind everyone of is this h at t minus a, that's the Heaviside function at a. So h at t minus a is a piecewise defined function. It's 1 if t is greater than a, and 0 if t is less than a. So really this h, the h function, is 1 if the argument is positive, and it's 0 if the argument is negative. So this is the Heaviside function shifted to a, so that if t is bigger than a, then the argument is positive, so you get a 1. And if t is less than a, then the argument is negative, so you get 0. So this is something that we'll need for our examples. Notice also we have the ERF here. This is the error function. That's something we talked about before, related to the heat kernel. Here we have 1 minus ERF. That's also known as ERF complement, the error function complement. ERF c of a over 2 square root of t. That's something that will come up as well. Let's do an example. Let's solve an initial value problem. So in this case, we have u prime prime minus u is equal to 1. And we want some initial conditions. So again, we'll just use our simple initial conditions. U at 0 is 1, U prime of 0 is equal to 1. Here, we just choose them both to be equal to 1 for simplicity. We want to have some initial conditions, but we want the computations to be nice. So you compute the Laplace transform of both sides. On the left, you have the Laplace transform of U double prime, which of course is s squared times the Laplace transform of U minus s at U s times U at 0 minus U prime of 0. That's the Laplace transform of U, and then, or U double prime rather. And from that we subtract the Laplace transform of U, which is right here. And this is going to be equal to the Laplace transform of 1, which if you go back to our little insert here, the Laplace transform of 1 is s to the negative 1, or 1 over s. So that's where that comes from. So what do we do now? Well, we can combine our Laplace transforms of U. So that's going to give us s squared minus 1 times the Laplace transform of U. And what does that leave us with? Well, U at 0 is 1, and U prime of 0 is 1. So we're left with a minus s minus 1. And we can add those to the other side. So on the right, we'll have 1 over s plus 1. On the left, we're left with s squared minus 1 quantity times the Laplace transform of U. We want to solve for the Laplace transform of U, so we just divide by that s squared minus 1, which is what we see over here. So that's the Laplace transform of U. We can, of course, reduce the fraction s plus 1 over s squared plus 1, because that's s plus 1 over s plus 1 times s minus 1. So it's just 1 over s minus 1. So that's where this term comes from. So the Laplace transform of U is equal to 1 over s times 1 over s squared minus 1 plus 1 over s minus 1. So now we can find U by using the inverse Laplace transform. So U is equal to the inverse Laplace transform of this product, 1 over s times 1 over s squared minus 1, plus the inverse Laplace transform of 1 over s minus 1. Again, we can get that from the table. That one is e to the t. So maybe once again we'll just color code some of these things. That's just e to the t. All right. So what about this Laplace transform of the product, or the inverse Laplace transform of the product? Well, we can use the convolution theorem to say that that's the convolution of the individual inverse Laplace transforms. So it's the inverse Laplace transform of 1 over s convolved with the inverse Laplace transform of 1 over s squared minus 1. And each one of those we know. The inverse Laplace transform of 1 over s is 1, and the inverse Laplace transform of 1 over s squared minus 1 is sine of t. So the inverse Laplace transform of 1 over s squared minus 1 is just, I think I said sine, but I mean hyperbolic sine of t. So we need to convolve these, but since one of these functions is 1, we're doing the convolution of 1 with hyperbolic sine. So since it's 1, that makes it just an integral, just the integral of hyperbolic sine of s from 0 to t, which is hyperbolic cosine of t minus 1. And then, of course, we don't want to forget this exponential here. So that's this one right there. So u is equal to the hyperbolic cosine of t minus 1 plus e to the t. Now notice this one, I didn't actually write it down, but that goes right, well, I shouldn't circle it because that'll look like a 0. So remember when you're doing a convolution, the convolution is going to be the integral from 0 to t of the first function at, and then it's going to be, in this case, t minus s times g of s ds. So the g of s in this case, that's our hyperbolic sine, that's this one. But the f in this case is just 1, so f at t minus s is just equal to 1. That's this one. So it just doesn't show up, so you just end up integrating hyperbolic sine. So that's how you get hyperbolic cosine, but you have to, it's a definite integral. The limits from t to 0. Hyperbolic cosine evaluated at 0 is 1, so that's where that 1 comes from. Okay, so we didn't actually need the convolution theorem in this case. We could have just used partial fractions, because this term here, 1 over s times s squared minus 1, which is this thing, that you wanted to evaluate right there, that we wanted the inverse Laplace transform. We can just simply, again, let me just color coordinate a little bit. So this term right here, 1 over s times s squared minus 1, that's this term. And you can write that out in a partial fractions expansion. And each one of these you can easily compute the inverse Laplace transform for. And you'll end up with minus 1 plus 1/2 e to the minus t plus 1/2 e to the positive t. And these exponential terms combine to give you the hyperbolic cosine. That's just the definition of hyperbolic cosine. So that's our example. For partial differential equations, we do things in basically the same way, but we treat x as constant and transform t into s. So the Laplace transform of a two-variable function u, so u is a function of a spatial variable x and a time variable t, is given by the same formula. It's just that you have an extra x floating around. But you just treat it as a fixed parameter, an unknown perhaps parameter, but it's just treated as constant. So the Laplace transform of u at x comma s is the integral from 0 to infinity of u at x comma t times e to the minus st dt. So otherwise it's the same. The time derivatives transform in exactly the same way, so we have the same formulas, but the spatial derivatives are not affected by the transformation. So the Laplace transform of the partial derivative with respect to x is just the partial derivative with respect to x of the Laplace transform. So basically the idea is you take the partial derivative out. So it converts t derivatives into multiplication by s, and x derivatives it leaves alone. So the value of this is that the Laplace transform turns a PDE in x and t into an ODE in terms of just x, because all of the time derivatives will be turned into multiplication. So let's look at an example. So here's an example of advection. So this is the advection equation. So we have I say u sub t, but of course I mean the partial derivative of u with respect to t plus some constant, let's just say that c is a positive constant, times the partial derivative of u with respect to x, and this is equal to 0. Here we're assuming that x is positive and t is positive. So we have some initial conditions as well. We have an initial condition that u at, let me label it this way, u at x comma 0 is equal to e to the negative x. So that's our initial condition. But we also have a boundary condition. So along the boundary where x is equal to 0, our value u is given by the sine function sine of t. So what we're going to do is we're going to compute the Laplace transform of both sides, and we're going to use that to solve for u. We have a partial differential equation. The Laplace transform will give us an ordinary differential equation in terms of x. And then we can just evaluate that using known methods. Or I say evaluate, solve for u using the known methods. So let capital U be the Laplace transform of lowercase u. So I'll try to make it clear which is capital U and which is lowercase u. So the Laplace transform on the left side is the Laplace transform of u partial t plus c times the Laplace transform of u partial x. And that's going to equal the Laplace transform of 0, which is just 0. Okay, so the Laplace transform of u sub t, we have that right here. That's this one. So that's s times the Laplace transform of u. So that's s times capital U minus the initial condition, minus u at x comma 0. Which is e to the minus x. That's our initial condition. So this is the Laplace transform of u partial t plus c times the Laplace transform of u partial x. Now remember, the Laplace transform leaves derivatives with respect to x alone. So the Laplace transform of lowercase u partial x is equal to the partial derivative with respect to x of capital U. And this equals 0. So now we have an ordinary differential equation. It's a first order ODE in terms of x. So let's just scroll up here like so. So now we can use the known methods to solve for this differential equation for capital U. So that's what we want to do. We want to solve for capital U. Okay, so how are we going to do that? Well, the first thing that I do is I just add this e to the minus x to the other side. This is our inhomogeneous term. Now we have c times the partial of u with respect to x plus s times u. So this is first order, it's linear. We divide by the c just to get a constant, just to get a 1 in front of the partial derivative term. And now we multiply by an integrating factor. The integrating factor in this case is e to the sx over c, where x is our variable. So if we do that, then this term on the left is the derivative of a product. It's the derivative with respect to x of e to the sx over c times u. And on the right, we have, of course, an exponential. It's sort of a busy-looking exponential, but it's nothing that we can't evaluate. So we integrate both sides with respect to x. So on the left, you just end up with that product, which was inside the derivative. So this term right here, that's just this term. But now we need to integrate this exponential. But it's just e to a constant times x. It's just that that constant is s over c minus 1. So we just integrate it using the usual rule for exponentials. So we leave the exponent alone, but then we divide by that exponent, which is over here. Now we also have a 1 over c in front of that. That 1 over c dates back all the way to this c right there. So just to keep track of it, that c, we divide by c, and it's right there. And so that's where this c is all this time. So that's that c right there. So if you simplify that, you just end up with 1 over s minus c in front. So all of this stuff right here, that's just 1 over s minus c. Okay, so then we have an e to the minus x, but there's also another factor of e to the s over c in there, which we've divided by. So let's see if we can keep track of all of this. So we had this factor right out in the front, e to the sx over c. So we've just divided by that. So there's another sx over c right there, which you can't even see. It went away. But then we also have this constant term here. And so that constant term, we divide that by e to the sx over c, or we multiply it by e to the minus sx over c. Now, speaking of the constant term, notice that it's a function of s. So when we say that it's a constant term, we're integrating with respect to x. So it's constant with respect to x. That means there are no x's here. But s is considered a constant with respect to x. So that constant that you get might have s's in it. So we can write it down as a function of s. It may or may not have s's in it. Okay, so long story short, we figured out what capital U is. It's this expression right here. Now it does have that constant function there, that constant function of s. How do we figure out what that is? Well, that's what our other condition is for. We have a boundary condition that will tell us what that is. So let's look at this boundary condition right there. So u at 0, t is equal to sine of t. Okay, well remember the Laplace transform doesn't affect x. So if we look at capital U, so this is despite how it might look, this is a capital U. Capital U of O comma S is equal to the Laplace transform of little u at O comma t. So this is the Laplace transform of little u at 0 comma t. But we know what that is. That's sine of t. So the Laplace transform of sine of t is 1 over s squared plus 1. So what that tells us is that gives us what capital U is when x is equal to 0. But we can actually get that from this formula as well, or rather from this formula as well. So if we just plug in x equals 0 into this formula, then this term becomes e to the 0, which is 1. And this term becomes e to the 0, which is 1. So if you plug in x equals 0 into capital U, you just get rid of the exponentials. So you have 1 over s minus c plus k at s. But this we know is equal to 1 over s squared plus 1. So that is that. So that means we can solve for k. K is a constant, but it's constant with respect to x, but it certainly has some s's in it. So you just solve for s, so that 1 over s squared plus 1 is there, and then we just subtract this 1 over s minus c there. Okay, so that's this one and that one. So this right here, this is k at s. But we know what it is now. So that means our capital U as a function of x and s is given by this formula right here. Notice that we mentioned that s is greater than c. That's just to make sure that this is defined. The Laplace transform is not always defined for every s. It's just defined for certain values of s. And in this case, it's defined for s greater than c. So now we can compute lowercase u by looking at the inverse Laplace transform of what we just computed. Okay, and that's the next computation that we look at. Now this particular computation is a little involved. So we want to compute the inverse Laplace transform of capital U, which is all of that stuff right there. So we want to find the inverse Laplace transform of each one of these terms. So we have 1 over s minus c times e to the negative x. And then we also have these terms here. So we have that ks term times e to the minus k over c quantity times s. So for this we want to use our Heaviside function. So multiplying by an exponential in the transform domain is the same as translation in the time domain. So this term right here corresponds, well, maybe I don't want to use that green. So this term right here, that corresponds to this Heaviside function. So really what we're looking at here is we're looking at, let's just go back to the table, which is up here. So we're looking at these functions here. So we have this thing right here. This is really what we're using. Maybe I don't want to use that color. Maybe I'll just use this color. So if you have a Laplace transform times e to the minus as, that's the same as translating the original function. And when you multiply it by the Heaviside function, that just means that it's going to be 0 up until the function starts. So the idea is that the function is 0 up until t is greater than 0, and we're shifting all of that to the right by a units. So that's what we're going to use here. So let's just go back down to our example right here. So we're multiplying by this e to the minus x over c. So in this case, a is equal to x over c. So that's why you get this translation by x over c. And you'll see that here too. So this is our t minus a. This one also, that's t minus a. And then here also you've got t minus a. And so on. So this 1 over s minus c, that's where we get this e to the c. So 1 over s minus c is e to the c times the variable, but it's a translated variable, so that's why there's a t minus a. 1 over s squared plus 1, that transforms into sine, but it's sine at t minus a. Now the one on the left here, this one, we don't have to translate. This is just 1 over s minus c times e to the minus x. There is an exponential here, as you can see, but that exponential doesn't have an s in it. There's no s in that exponential. So in terms of the Laplace transform, that's constant. So that just comes out as that e to the negative x there. So let me just, so this is e to the minus x, that's constant. There's no s's there. So it's just a constant, it comes out. Then we have the 1 over s minus c, and that, the inverse Laplace transform of 1 over s minus c, is e to the ct. So now what we have is we have found our function little u, which is the solution to the advection equation. As you can see, it has this heaviside function in it, and that's not for no reason. Advection equations, or solutions to the advection equation, change depending on whether or not x is less than ct or x is greater than ct. So remember that solutions are these right-traveling waves, and so they behave differently depending on whether you're to the left or the right of the characteristic curves. So if x is less than ct, what does that mean? That means that this term right here, so this term right here, t minus x over c, we can rewrite that as the heaviside function, or h at ct minus x. So if x is less than ct, then that means that this term becomes 1. So if this heaviside function right here is 1, then you just add everything together. So this exponential will cancel with that exponential. And so if x is less than ct, you just end up with this sine term. You just end up with that sine term, which I've rewritten here just so it looks like the right traveling wave. On the other hand, if x is greater than ct, then this term becomes 0. And so you're just left with the exponential, which you see here. And then this one's rewritten here so it looks like a right traveling wave. So that's the solution to that advection problem. The previous example was a first-order partial differential equation, so let's look at a second-order partial differential equation. So let's look at this diffusion problem. The partial derivative of u with respect to t equals the second partial derivative of u with respect to x. So this is an equation with boundary, so x is greater than or equal to 0. So we need not only initial condition, but we also need some sort of boundary. So we have an initial condition here, and we have a boundary condition here. We're keeping it quite general at the moment by letting the boundary condition just be u at 0 comma t is equal to some function f at t, where f will have whatever properties we need. It can be as differentiable as we want it to be. So let's compute the Laplace transform of both sides. So on the left, we have the Laplace transform of the first time derivative. So that's going to be s at the Laplace transform of u, which again we'll call capital U just like before. So it's s times capital U minus the initial condition. And we're being a little bit easy on ourselves here, and we're letting the initial condition be 0. And this is going to be equal to the Laplace transform of the second x derivative. But remember, the Laplace transform, it doesn't exactly ignore the second derivative, but it doesn't transform it. So the Laplace transform of the second partial derivative is the second partial derivative with respect to x of the Laplace transform. So it's capital U sub xx. So we have here a second order differential equation in terms of x, but it's an ordinary differential equation in terms of x. So this is something that we know how to find, or we know how to solve. So we find the characteristic equation is r squared minus s equals 0. So r, the roots of the characteristic equation, are plus or minus the square root of s. So that gives us our general solution here. Now, notice that the constants are functions of s. That's because, again, we're solving this differential equation in terms of x only, so the coefficients, which are constants with respect to x, might have s's in them. Now we want our solution lowercase u to be a bounded function. So what we're going to do is we're going to set c2 of s be equal to 0. Now why are we doing that? Well, importantly, if you have a function that has a Laplace transform, then it's necessarily the case that the Laplace transform must decay as s goes to infinity. The only way that that can happen is if this term isn't present, because that term is not going to decay. So the only way that we can have a bounded function in the time domain that will have this as a Laplace transform is if we set c2 at s equals 0. So that term goes away. So that means capital U is just equal to this term. So it's C1 at S times the exponential to the so it's e to the negative x times the square root of s. Now how do we figure out what C1 is? For that we need our boundary condition. So the Laplace transform of lowercase u at 0, t is equal to the Laplace transform of this function little f of t. And so we're just going to call that capital F at s. That's the Laplace transform of little f. Now this Laplace transform of lowercase u at 0, t is the same thing as capital U at 0, s. And we know what that is. That's C1 at s times e to the negative x times the square root of s, but x is equal to 0 now. So we're just going to have a 0 up here. So that means it's e to the 0 is 1. So capital U, so this is capital U or uppercase U, at 0, s is equal to C1, but we also know it's equal to f at s. So that means that that coefficient is capital F at s. So capital U at x, s is equal to capital F, the Laplace transform of little f, times e to the negative x square root of s. So now to find the lowercase u, we need the inverse Laplace transform of that. But capital U is the product of two Laplace transforms. So that means the inverse Laplace transform is going to be a convolution. So it's the convolution of two functions, f and g. Now f is this f right here. It's the little f from our boundary condition. This g is something I'm just introducing now. But g is whatever function gives me this as a Laplace transform. So L of g, Laplace transform of g, is e to the negative x over s. And Laplace transform of little f is capital F. That we already decided. So how do we figure out what g is? G is the inverse Laplace transform of e to the negative x over s, not over s. G is the inverse Laplace transform of e to the negative x times the square root of s, and we use a table for that. So here's that same table. This is the same table as before. So this is the same table. From Logan. So we just look in the table for the relevant entry, which is this entry right here, e to the negative a square root of s. Now in this particular case, a is equal to x. And this square root of pi isn't there, so that means whatever our answer is, we're going to have to divide by the square root of pi. And that's exactly what we do here. So we just rewrite everything that we already have. Little u at x, t is equal to the inverse Laplace transform of this product. So this is the Laplace transform of f times the Laplace transform of g. So u is equal to f convolved with g, and g is just this expression right here. X over 2t to the 3 halves times the exponential of minus a squared, but a is equal to x, so it's x squared over 4t. And remember, we have to just divide by that square root of pi, so that's where that comes from. Okay. So this f was given as the initial condition, and this g we were able to get from the table. So what does that tell us? Well, u is the convolution of f with g, so we just write the convolution, the integral from 0 to t of f at t minus v times g at x comma v dv, and that's this expression. Now this is not an expression we're going to be able to simplify. First of all, we don't know what f is, but also this isn't going to have an elementary antiderivative, so we're not really going to be able to simplify it beyond that. So let's look at another example of the diffusion problem. In this case, let's change our initial condition and boundary conditions around. So now we have an initial condition, which is general, and our boundary condition is going to just be 0. But otherwise, it's the same differential equation, u sub t equals u sub xx. Okay, so we want to proceed in the same way that we did before. The only difference here is that now we have an initial condition, which is a general function, but our boundary condition is gone. All right, so we compute the Laplace transform on both sides, and on the left we get the same thing as before. We get s times capital U minus the initial condition. Only now the initial condition is not 0, so this phi of x shows up right there. On the right-hand side, we have the Laplace transform of the second derivative with respect to x. So of course, that's the second derivative with respect to x of the Laplace transform. So once again, we have a linear second-order ODE in terms of x. It's not homogeneous. Here's our phi right there as well. So we get it in the standard form. So it's u sub xx minus s times u equals the opposite of phi at x. And once again, the complementary solution is the same. It's c1 at s times e to the minus square root of s at x plus c2 at s times e to the square root of s times x. So it's right there. That's our complementary solution. So we need to find a particular solution. And for that, we can use a variation of parameters. So I've set that up here. So you can see what we've done here. So this is the formula that you can use to find the particular solution. Notice the Wronskian appears here. The Wronskian is easy to compute in this case. It's just 2 times the square root of s because the exponents come down. Since we have e to the minus square root of s times x and e to the positive square root of s times x, all of these terms sort of simplify, so you just end up with the square root of s plus the square root of s, which you see there. So this is the formula that you use. I won't go into the details of it so much, but notice that you have the opposite sign of the first solution times the integral of the second solution times the inhomogeneous term divided by the Wronskian dx. And then here it's the second solution and it's the integral of the first solution times the inhomogeneous part divided by the Wronskian dx and so on. So we actually can't compute these because we don't know what phi is, but you can use, we need an antiderivative, so you can use the fundamental theorem of calculus to write that as a definite integral, which I've done here. So we have capital U is equal to the complementary solution plus a particular solution. Now this is going to be hard to compute without a specific phi. We could leave it in very general terms, but it's not going to be very useful for us. So what we're going to do is we're just going to solve this for a particular phi. We'll choose a phi that makes our life easy. So choose phi to be equal to 1. So for simplicity, and you'll see it's not even that simple. When I say simplicity, it's not a lot of simplicity. So for example, choose phi of y equals 1 for all y. So in that case, we just put a 1 there and a 1 there. And so we end up with capital U is equal to the complementary solution plus this particular solution. Now these are things that we can actually evaluate because this is just an exponential. It's easy to think that because there's a square root of s that we have a problem. However, this is an integral with respect to y. So these are just e to the constant times y. So those are easy to integrate. And I won't go through all the details of the computation, but you end up with more complementary parts, so you just have those here. So you have u, capital U, is equal to the complementary part plus the particular solution, which is 1 over s. Now again, we have to do the same sort of thing that we did before. In order for this to be a bounded function, in order for lowercase u to be a bounded function, this Laplace transform needs to decay as s goes to infinity. This term decays, but this one does not, so we need to get rid of it. The boundary condition will tell us what C1 is. So you can just look at the Laplace transform capital U at OS, and that's going to give us the C1 of S plus 1 over S, because at 0, when x is equal to 0, this term is just 1. So you have C1 at S plus 1 over S, and this has to be equal to our boundary condition, which is 0. The Laplace transform of 0 is 0. So that tells us that C1 of S is minus 1 over S, which we have here. So now we can compute the inverse Laplace transform. So we have the inverse Laplace transform of minus 1 over s e to the minus x square root of s plus the inverse Laplace transform of 1 over s. Now the inverse Laplace transform of 1 over s, that's an easy one, that's just 1. Now for this one, we have to go back to our table. So let's just go back to our table, which is all the way up here, and it's this one. See, it's 1 over s times e to the minus a square root of s. So again, a is just going to be x in our case. So then we have this 1 minus ERF, which is the ERF complement. ERF stands for error function. So we just have that right here, 1 minus ERF. So there we have our 1 over s, and there's our e to the minus a square root of s. So we just end up with 1 minus ERF. Now, as I mentioned, 1 minus ERF is the complementary error function. ERF stands for error function. So we can actually just write all this out. So we have a minus, the inverse Laplace transform, which is here, plus a 1. But that's minus 1 plus 1 cancels, and you just end up with the opposite of the error function, which is just the error function. And we actually know what that is. There's a formula for that. Again, this is not something we're going to be able to actually evaluate exactly because we don't have an elementary antiderivative. But you could evaluate it using a computer to any degree of accuracy you wanted if you picked a specific value of x and t. And this is a function of x and t. So that's our example. Now you can check that this actually is a solution, which is something that you should always do. It would have been very easy to make a mistake somewhere along the way. So we can just check to make sure that this is a solution. So here's our claimed solution. You can just go ahead and we can't compute the value of the lowercase u exactly, but we can sure differentiate it just using the fundamental theorem of calculus. So we differentiate it with respect to t, and then you end up replacing r with t, or rather you end up with replacing r with the upper limit of integration, and then you differentiate that with respect to t, is what I meant to say. So this upper limit of integration just goes to where the r is, and then you multiply by the derivative of that with respect to t. And I won't go through all the details, but you can just check the arithmetic here, and you can see that sure enough, these two things are equal, which is what we wanted them to be. You can also check the boundary conditions, u at x comma 0. So if you put t equals 0 here, then you're looking at the limit as you're looking at an improper integral from 0 to infinity. So as t goes to 0, the upper limit goes to infinity. This actually is a probability density function now that you're integrating, so you just end up with 1. And when x is equal to 0, then you have a 0 in the upper limit. So the integral from 0 to 0 is 0. So it does satisfy the boundary conditions. Now at some point there we made a simplifying assumption where we chose phi to be equal to 1 just to make things easier. As you can see, even with that choice of phi, the computations were not trivial. Let's look at another example. So we've looked at an example of advection, we've looked at the heat equation or the diffusion equation. Let's look at the wave equation. So u sub tt equals c squared u sub xx. So let's let u at 0t be equal to e minus t. So this is our boundary condition here. Let's just label it boundary condition. And we have two initial conditions now. We need two initial conditions because we have two time derivatives. All right, so again, we're going to let capital U be the Laplace transform of lowercase u, just like before. All right, so the Laplace transform of both sides. On the left, we have the second derivative with respect to t of u. So that's going to give us s squared times capital U minus s times lowercase u at x comma 0, which is our first initial condition, which is 1. And then we're going to have minus the first partial derivative of u with respect to t at x comma 0. This is our second initial condition, which is just 0. And again, we just choose 0 to make things a little bit easier to compute. This will be equal to the Laplace transform of the right-hand side, which is c squared, because that's a constant, times the second partial with respect to x of capital U. All right. So once again, we've turned this partial differential equation into an ordinary differential equation in terms of just x. So once again, it's second order, it's linear, so we can get it into standard form. You can find the characteristic equation. In this case, it's a little bit nicer because there are no square roots. So you get that the complementary solution is c1s times e to the sx over c plus c2s times e to the minus sx over c. All right, so let's scroll up so we can see more of this problem. So the first thing to do is to find the particular solution again. So we've already found the complementary solution, we found the characteristic equation, we found the roots to the characteristic equation, and that gave us the complementary solution. Okay, that's fine. That's the solution to the homogeneous equation. But now we need the particular solution. So again, we can use a variation of parameters. For this particular one, we could have just gotten away with using something like undetermined coefficients, but as long as it's already here. So we need the Wronskian, which you can easily compute. It's minus 2s over c. And then you can just go ahead and compute these. And in this particular case, everything's quite straightforward to compute. And what you end up with is you end up with the particular solution is equal to 1 over s minus some terms which you can combine with the complementary solution. Now again, I've got these k1 and k2 here. These are the constants of integration. You can see them showing up right here and right here. These are constants of integration, but they might have s's in them. So k1 is some function of s, and k2 is some function of s. But we can just combine these with the complementary solution because these are terms from the complementary solution. So you can just combine them. So you get that your capital U is equal to some constant function with respect to x, but it might have some s's in it. So it's c1 of s times e to the sx over c plus c2s e to the minus sx over c plus 1 over s, our particular solution. Now again, it's the same deal. We want to have a bounded solution, so this term needs to go away. So you just choose c1 at s equals 0. The boundary condition says that lowercase u at 0 comma t is equal to e to the negative t. So if we compute the Laplace transform of that, let's just scroll up a bit. So if you compute the Laplace transform of the boundary condition, you get that the Laplace transform of e to the minus t is 1 over s plus 1. However, the Laplace transform of lowercase u at 0 comma t is uppercase u at 0 comma s. And we have a formula for that. It's right here. So that's c2 at s times e to the minus sx over c. So in this case, we're looking at x equals 0. We're looking at x equals 0. So this term right here, that's just going to be e to the 0 as 1. So you're just going to have the c2 at s plus 1 over s. But so this is capital U at 0 comma s, but this needs to equal 1 over s plus 1. It needs to equal this term right here. So c2 at s is equal to 1 over s plus 1 minus 1 over s. So that tells us that capital U at x comma s is given by this formula right here. So there's the 1 over s there, and then we have this 1 over s here is that 1 over s, and then we just have this other 1 over s floating around, which is the particular solution. So let me just do some highlighting again. So this 1 over s is that 1 over s is that 1 over s. Because we're finding c2 of s, which is something that we're multiplying, by this e to the minus sx over c term. So I don't think I've used blue yet. So this term right here, that's this term. Now we still have this 1 over s, which is a complementary term. So this 1 over s right there, not the complementary, that's our particular solution. That 1 over s is the same as that 1 over s, which is that 1 over s. Okay, so we have to do a little bit of work to figure out exactly what the inverse Laplace transform is here, but that's something that we can do, and that's something that I have done. So here we have an e to the minus sx over c. So that is multiplying by an exponential on the transform side. So on the original side, that corresponds to a translation. So I won't go through all of the details of the computations, but then you can work out based on what 1 over s plus 1 is, the inverse Laplace transform of that is going to be an exponential. It's e to the minus t, but then you just have to translate it. And similarly here, 1 over s, that's e to the 0 or e to the 1. So when you translate that, you just end up with 1. This one, rather. Then you still have that one there. So this 1 over s from the particular solution, the inverse Laplace transform of that is that one, which is right there. Okay. So this gives us our solution. Notice it is defined in terms of a Heaviside function. So that gives us a change in the nature of the solution, and that happens exactly when t is equal to x over c, or x is equal to tc. So again, the nature of the solution changes when you get to the characteristic curve. But you can check that it's a solution. We need to show that this satisfies the wave equation, and we also want to check that it satisfies the boundary condition and the initial conditions. But you have to do these separately. So if t is greater than x over c, then in that case, this term right here, if t is greater than x over c, then that's the Heaviside function evaluated at a positive number, so it's 1. So you end up with the exponential minus 1 plus 1, so you just end up with the exponential term right there. If t is less than xc, then this term cancels, that's 0. So this whole thing goes away, so you're just left with 1. So it starts off as 1 for a while, and then as soon as t gets to x over c, then it changes to e to the minus t plus x over c. So you can just check for each one of these that it satisfies the initial condition, and you also, or rather, that you can check for each one of these that it satisfies the differential equation, and you also need to check that they satisfy the boundary conditions and the initial conditions, which you can easily do.